Hey there, folks. I hope that you're doing well, you're staying warm, and you're starting to get to the swing of things, both for this class as well as for SOS 232. I know the online format is a little bit new for many of you all, and if you're feeling a little bit cautious about things, don't worry. Swing in, ask me about things in office hours, and I'll get you squared away. But now, as you all sort of gotten a little bit acquainted both to each other as well as with the course and started to look at the general social survey in terms of a questionnaire system, we're going to dig a little bit deeper into our understanding of data and statistics, beginning with our univariate analysis with basically one variable, and looking into quantitative or numerical data, things like age, number of years of education, and other things that are more numerical and can be done in a computational structure. What I mean about that, we'll see. So let's step inside into the lecture notes and we'll get started. If it sounds okay with you, let's begin. So, as we dig into sort of our social statistics structure and everything that goes alongside with it, we can look at what's really going on here and seeing that we're going to look into what we call measures of central tendency, so the mean, median, and mode, as well as our measures of dispersion, the minimum, maximum, and the standard deviation. These descriptive statistics, as we'll come to learn, are only appropriate tools for using to summarize data, where the variables are continuous or essentially what we call numeric in nature. We'll also explore graphs and how they help describe the story behind our data and sort of explain really what's going on. So, it's a quick outline. We'll look at some descriptive statistics, talk about numeric data in general, including the measure of center, mean, median, mode, as well as measures of dispersion, the minimum, maximum, a five-number summary that we'll talk about, the standard deviation as well, and we'll look into some graphical representations, such as histogram density plots, box plots, and the certain properties behind them, the shape, the skewness, these things. Now, descriptive statistics really the best way to describe it is we want to summarize our data. We want to take our data and basically, instead of just having these observations and talk about these individuals at an individual level, summarize them into a an understanding of how the entire population or how the entire sample that we'll eventually work with actually helps us summarize. This is a form of what we call data reduction. And data reduction is basically just reducing all the numbers into a few of them that really help explain what's going on. Right now, we'll talk about univariate statistics. And these are statistics involving a single variable or survey question. And we'll explain right now with this idea of numeric data. And numeric data for surveys is basically survey questions where the response results in an actual number report. Now, be careful. When we talk about number reports, there's a nuance behind that. Some examples, we'll see what's going on. So things like respondent's age, respondent's education level, but not necessarily in terms of high school, college, so on, but how many years of formal schooling do you have? So this explains that, or at least believes that there's a difference between maybe 11 years of formal schooling and 10 years of formal schooling. Also, we have something like family income or the TV hours, television habits for someone like on average. How much TV do you watch on a given day? Now, be careful, as we're going to talk about this a little bit more. These variables are going to be given in terms of a number, but numbers often are used in other components for the general social survey. Typically, we'll have certain labels attached, and we can analyze those things effectively that way. But one of the things we'll talk about is, does it make sense to do mathematical operations and eventually what we call an average? An average age would make sense, so we can think of this as more of a numeric or continuous data. Now, in exploring these numerical variables, we want to discuss the properties of the distribution or pattern of a variable, which tells us what values of a variable takes and how often it does give us these certain values. Such properties are like the center of the data, the spread and the variability of the data, the shape of the graph, and outliers or unusual observations from our data itself. So measures of central tendency, this is the average thing I was talking about, is really a measure of typicalness. They help provide a one number report on the distributions in the middle or the center of the points. And there's three main measures of center for you all. There's the mean, there's the median, and there's the mode. A lot of you all probably have heard this stuff before, either in grade school or you've heard it in some other class. And if so, great. If not, we're going to make all these things feel one, more than just a number, and two, filling up the foundational aspects of how to analyze this stuff as we go a little bit further down the road. Now, one of the basic elements of the mean is really just the average of how many people responded to a particular numeric survey question. Mean, we'll see this in this sort of formula form where it's like this little sigma. It's a Greek letter sigma. And then for the capital sigma, it's usually think of as sum. So adding them all up. So these x of i's are basically our observations for each of these individuals. So if I said x sub 3, so that's like x with a little 3 at the bottom, all that's saying is that that's the person number 3 in our survey. And little n is then the total number of people who responded in this question. So basically, the number of people measured, surveyed, and our sample size. Now, many people might use the symbols for the mean, thinking like this mu symbol, it looks like an M, or you might see the population mean, or that's for population mean for the sample mean. You might see this sort of X with a bar in front of it, on top of it, where it's called X bar, for the mean of our survey and sample. In this class, we're not going to use those symbols when I'm writing these things up in our data. One of the reasons why is because, well, the symbols are useful. And I think having an understanding what these symbols are supposed to be is important to being, a social scientist going into some sort of data analysis or being able to read this stuff a little bit. To talk about it, we usually don't say X bar. We usually just call it a mean. So we'll call it what it is. We'll say, you can say sample mean if you'd like, but for the most part, we'll consider just the mean of our survey. And we'll go with the understanding that anytime we're talking about a general social survey or any sort of survey data, we're thinking of this as sample data because typically we don't have the time, the people, the resources in general to get every single person in the population. So mean is all right by me. Then we have this definition where we want to look at maybe not just the average, but what is the middle number? Where do about 50% of people seem to be on each side? Now, sometimes it is the mean, but oftentimes it's not. So we want to figure out some sort of value that denotes where half the respondents are at one side and where the other half are. So that sort of cutoff point is known as the median. Or shorter, you might see as MDN. We'll organize all the values into this array from low to high. What I mean by array, just a list of values. If the number of observations is odd, then the median is really just the one that's right in the middle, only they go from smallest to largest. If it's even, then I'll often take the average of the two middle observations, and that makes it to a median itself. Again, I'm using this sort of formal terminology, but really the median is just the middle number that splits the data into half, where 50% is lower, 50% is higher. Some people will use these fancy terms like eta for the Greek letter for population mean and a capital M for the survey or sample median. In this class, I want you to instead you could say MDN, or you could just call it the median, and that'll work here too. I want you all to avoid using the capital letter M, as it may be confusing for non-stats folks, because they might think you're actually talking about the mean. Now, you all, savvy stats, social science folks, they say, well, there are other places where they'll use capital M for the median. And that's true. It's a good reminder one, you're learning this stuff right now as well, but two, you want to talk about this to other people who may not have the stats savviness that you're about to pick up. So talking about these things beyond the symbols are very, very important. And we want to be able to use things like the median effectively. Because all of this is about sort of communicating what's really going on. And the last part is the elements, the mode. The mode is really just the value that happens most often. The mode formula is really just, find out how many unique observations you have, unique numbers or whatnot. If there is no value, if all of them just happen only once or all of them happen exactly twice, and so on, the data would have no mode. But often it does. Usually, when you have a large enough sample size, there's at least a couple values that happen more often than others. And so, if you have that case, then you find out how often does each unique value happen. So, if I said age, there might be a bunch of people who are 21, 22, 23, and so on, but maybe most people are 25. Then the mode would be the one with the highest frequency, the most number of observations or individuals. Now, you could have something like the same number of people being 25 as well as 27. And if that's the case, then they're both considered a mode in our analysis. That was a lot. Go ahead, take a short break, take a breather. And as you get ready and get going to the next piece, take a quick little check for your knowledge to make sure you feel good with what you've learned so far. Scrolling through the people who are exploring these things and trying these out. Here's the end of quiz. Let's get on to the next piece. Now, there's more to the data than just the measure of center. You could have two sets of data with the same means, the same medians, and actually the same modes, but very different patterns. And so you have to be able to distinguish what's really going on. Another way to help distinguish that is through these measures of dispersion. Now, measures of dispersion are basically this descriptive univariate statistic that's used with numeric data. They'll summarize the spread or the variability of the distribution. Basically, how much does the data vary? Not everybody is the same age. Not everybody is the same height. Not everybody has the same GPA. There are differences typically in a data set. So we want to sort of be able to find some sort of metric that helps explain where those observations or those values seem to vary among a population. We'll look at also through these summaries of the minimum, the maximum. We'll look at this thing called the standard deviation, and then these quartiles in the 5-number summary. Now, reporting the tail ends of the distribution, the lowest and the highest reported values, these are the minimum and the maximum. And the lowest, you find the highest values, and usually so the lowest reported value is blank, the highest reported value is blank. I typically urge you all, pull out your thesaurus, pull out your thought, that brilliant brain of yours, and think of something that's a way to describe, even lowest and highest work, but like avoid minimum and maximum. And again, we can use our specific special stats terms whenever we need to, but we also want to communicate these things to others. And sometimes it feels like just talking a bunch of jargon type values feels very computer robotic and not really our human tone. Again, when we're writing about this stuff, when we're talking about this stuff, we're looking to try to be able to explain what's going on to individuals who have only a very limited stats understanding because they took stats 20 years ago and they forgot a bunch of it, or they haven't really had a formal stats course before. So we want to still be able to talk to them when we're talking about this data analysis stuff. Now, if I want to talk about summarizing these tail ends of the distribution for something like TV hours from the 2018 Global General Social Survey on television hours. Well, the minimum 0, maximum 24. That means the lowest reported number of hours was 0 hours of TV watch, while the highest number of hours was someone apparently had the TV on all day and all night for 24 hours being reported. Side note, definitely look up the lady from the 1980s who was like, who knows? We might lose all this understanding of what television and culture was, and I need to record it. So she ended up recording years of just television and has like an archive of like old commercials, old understanding of a bunch of stuff. And it was really cool to sort of see that like this stuff is kind of prepared and saved out into the world. Now, as we try to figure out how to, analyze this stuff, we'll often want to figure out, how do I write about it? How do I describe it beyond just minimum and maximum? Well, you might want to say people who didn't watch, there are people who didn't watch any television per day. And no, when I say these things, I often will put the stats jargon, the min equaling 0 in parentheses. So if you want to go really formal and really statistical, you can still have those terms. Putting them in parentheses allows the reader to understand that this is the stats formatting that you've just now explained when you're writing these things up in like regular people words. And then you say, well, there are others who reported watching television for the entire 24 hours each day. So maximum 24. And I'm still noting a minimum maximum. I don't have to necessarily say it in those words. And this is a way we can sort of up our writing game as well. Now, from reporting the minimum and maximum from one of our measures of spread, we're already reporting a fuller picture of the distribution of our audience than just reporting a measure of center. It's not just the average, but really how far do we range? Now, the minimum and maximum are really good. We love a way to figure out how to discuss the varied or spread out the data is. And one way to talk about this measure of spread is the standard deviation. The standard deviation looks scary. If you look at this, I feel you're probably throwing up in your mouth a little bit. I get it. That's fine. I feel you. This idea is taking these square differences and basically saying, all right, how far are these values away from the actual mean itself? I use X bar here, sample mean. And we'll do something that looks actually kind of like, if I go really mathy, kind of like a distance formula. It basically makes a distance formula out of things. But not just a distance formula, it's almost like an average distance formula. And that's what standard deviation essentially gives us, a sense of an average standard, or the standard deviation is like an average distance formula. How far away on average are our data away from the sample mean? Now, that measure looks really nasty. The formula looks really nasty. You don't have to do that in this class. One of the things I want you to like fully hold on to is that for most part, most of our actual numerical analyses, the number crunching, is done with Jamovi. It's one of the reasons why we like using really sophisticated packages is like if you know how to use the commands, you can actually do a lot with it. Instead of having to use a calculator, having to do stuff by hand, I don't really care about those things, and neither do most people. There'll be a couple of comparisons we'll be working with, but for the most part, Jamovi's going to save us a lot of time, a lot of hassle, and probably a lot of obscenities. So essentially what I was saying, basic elements of the standard deviation, that most people fall from the mean, and it gives us an average measure of how far the observations differ from our average value. Now, reporting the standard deviation, please remember it's not a standalone statistic. You need to make sure you report not just the standard deviation, but the mean as well, because it gives us an idea of the center as well as how spread out it is. So, standard deviation measures the spread about the mean and should only be used when the mean is the most appropriate measure of center. We'll explain in a couple slides from here and now that like sometimes the mean isn't the most useful. Sometimes it's more the median. But when you talk about the mean, you want to use the standard deviation to help to detail the spread as well. Fun fact, fun for me, big old math nerd, is that actually one of the reasons why we like describing the mean as well as how spread it out it is that I could add one standard deviation, two standard deviations, one standard deviation below, two standard deviations below, and at least 75% of the data has to be within this range of all of our values. So if I were to say that your average age was 25, but a standard deviation was 2 years, then 75% of people for their ages need to be between two standard deviations below would be 23, 21. Two standard deviations above would have to be 27, 29. So 21 to 29 years old, at least 75%. Now, if the shape is actually a bell, then we get about 95% of the data. And that's really, really nice because that means we know just about what most people seem to be ranging or varying by. You can also explore the spread of numerical variables by looking at percentiles. Percentiles are something that you're probably comfortable with because you had to deal with these things at some point when you took standardized tests, when you looked at ASVAB scores, things like that. There's a p% of data, which is like basically saying that you scored that your response is higher than p% of all observations ever recorded. Now we use percentiles often, but some of them we use more often than others. And three big ones outside the minimum and maximum are known as our 25th percentile, our 50th percentile, and 75th percentile, our quartiles, so breaking the data up into quarters. The 50th percentile is actually what our median is. It splits the data in half. We broke the data into lower halves and upper halves. Then the median of our lower half of data, is Q1, or the 25th percentile. And then the upper half is Q3, or the 75th percentile. And breaking it down splits up the data, what we call a 5-number summary, where we include the minimum, Q1, median, Q3, and maximum. And in doing so, we essentially know the breaks where each quarter of our data seems to be varying. We know our minimum and the lower quartile, then we know 25% has to range between here. Between the lower quartile and the median, or Q1, is here. 25% here and 25% here. And Jamovi can actually get you the 5-number summary using the same process you might use for the mean standard deviation, get us all of these values. So we don't have to calculate anything on our own. So based on this Jamovi output, what would the 5-number summary of the data be? Looks like there is, I go through, there's 25th percentile is 1, 50th percentile is 2, 75th percentile is 4, and the minimum 0, maximum 24. And get all the values right here. I also can get the median given here, which is also the 50th percentile, and so they should match up without any issue. Now, that was descriptive statistics through numerical summaries. But a lot of data is really, really enhanced by having a good picture or graphic that helps explain. In statistics, we use our numerical summaries often, but we often also want the visual representations of graphs. Effective graphs tell a story. By having appropriate labels and titles to describe what's going on and enough ink that tells us what we need to see, it gives us an idea of where values seem to be in terms of frequencies and so on. The properties of these shapes of graphs, these shapes of skewedness, the shape is really one of the more important features of data. It tells us what it looks like. Things like bell shapes, triangular shapes, uniform, right skew, J shape, reverse J shape. These are a bunch of different possible shapes that could come from there. We also have something like skewedness. And skewedness is a property that describes how evenly balanced the data is over spread. Now, in this skewedness process, we can figure out whether something is skewed by the tail of the distribution, basically where the data seems to sort of peter out and go away. If there's data that seems to be dipping, maybe there's a bunch of data here, but eventually dips down into this area, we think this is skewed to the right. It's basically more than most of the data is on the right side and is sort of dipping down this way. So more than half the data is going to be on the left of this sort of peak. So on the left side, and there's a lot of data that's sort of like dipping down and not doing much. If it's skewed to the left, then we have a tail on the left side. More than half the data is then it's really going down on this end. And we can sort of see that there's a big hump here where the data seems to be a good chunk, maybe a little bit to the right, with the rest of them sort of dipping down. And the distribution is roughly symmetrical. The left and right sides, basically, if I split down the middle, look like mirror images. So something like this bimodal distribution I had here, this bell-shaped triangular uniform stuff, all kind of fits what we're talking about. Now, the bell curve or the normal distribution is also another type of distribution that is really, really nice that we will eventually want to use. Normal distribution is often known as a bell curve, and it finds itself naturally representing a whole bunch of things in the real world, like height distribution, for example. One nice property is that it seems pretty symmetrical. If I were to split this down the middle, it looks like almost the same on both sides. Also, about 95% of values fall within 2 standard deviations of the mean, like I talked about before. We'll use the bell curve indirectly to prove our research results when we jump into our statistical significance, basically modules 4 through 7. Normal distributions are symmetrical distributions, and one of the nice parts about symmetrical distributions, the mean, the median, and the mode are all equal to each other. Skewed distributions typically don't have those three actually equal to each other. So that's one thing to keep in mind when you have this sort of skewedness. When they're not very equal, especially if there's a big difference, you probably have a lot of skewedness going on. If something is negative skewed, what that means, or skewed to the left, and honestly, I prefer talking about it skewed to the left versus skewed to the right. If it's skewed to the left, it means that we have values here. We have some really small values that seem to be pulling the mean on average. It pulls it in the negative direction, or at least in the lower direction, and makes the mean smaller than really most of the data. If there's a positive skew, or skew to the right, the mean is actually going to get pulled up. So if I had a bunch of people who, how far away do you live from EKU? And we have like so many miles, and then we have someone who's like 3,000 miles away because they're taking this online course and they're in some place far away. Then it seems like that would actually make the average a lot higher, even though most people are probably within, let's say, 60 miles from EKU. Now, comparing the mean and median for the 2018 data and TV hours, what I just consider, I don't have to look at the graphs or anything, would we consider this distribution negatively or positively skewed? Let's see. The mean is 2.94, the median is 2. Is 2.94 bigger or smaller than 2? I think it's bigger. And because it's bigger, we think that there are more likely values that are pulling the mean up above the median. There are some folks who actually have TV on 24 hours a day, and that brings the average a little bit higher. So comparing the mean and median in the future will help us determine the average of what a good measure of this would be. So for example, the average TV amount was just under 3 hours a day. It's worth noting that half the respondents were watching about 2 hours of TV or less. And it's important information to share with this interactive public or policymakers so that they can make informed decisions. Reminder, honesty, truthfulness in reporting is an important scientific skill, being able to really make what's really going on come to life, and through a sort of honest representation, allows people to sort of see both sides, not just the mean, but the median as well helps us. Now, I talked about certain graphics that are useful, and histogram is a popular method for displaying this quantitative variable. Histograms are useful because they take on many values, and as a graph, it shows how often variables seem to occur, and they fall in sort of like these frequencies. This thing we'll call it as a density, but for right now, think of it just as frequencies, how often they happen. These ranges are typically determined by software. We could adjust these class intervals if we wanted different ranges if we needed to. Be careful. If you do find yourself adjusting these ranges, they might tell a different story as they could change the shape of your data. Now, we'll often want to see how the things get put together. So sometimes they'll lump together between 15 and 25 and 35 and 55-year-olds. And so like we could see how those things seem to be put together. Responses are between 0 and 10 hours. In this case, it looks like 0 and 10 hours. By the time I get to 10, right here, I don't see a lot of data beyond 10 hours. And so it totally gives us a good understanding that most people seem to be going between 0 and 10 hours for television watching. Beyond that, not a lot. There are some, but it's definitely limited. To help the picture in the shape, we could also include something called a density plot, which basically tries to shape the histogram to look like a graph, and one that kind of looks like one of those you might look in like algebra class. I know, awful, terrible. Put it together, you get something called a histogram density plot. And that helps us tell the story of where the data seems to be taking shape, literally. You can also explore data through box plots. Box plots take the information from a 5-number summary and help us see how the data breaks up. First, we'll draw a rectangular box from the ends at sort of Q1 and Q3, the first and third quartiles. The median of the data is usually shown as the line that splits up the box. Whiskers are drawn from the ends of the rectangle that extend either to the minimum and the maximum, or to values of formulas that determine the best represent how far most of the data should extend. These are called adjacent values. We'll let Jamobi determine that for us. But if there are observations that are going beyond these whiskers, we'll consider them to be possible outliers, and Jamobi will represent them with dots. The box plot can also, as another example of our TV hours with dots. Then in this structure we have over here, then as the dots go down up, it seems like television hours, most of them, like I said, were about 0 to 10 hours, but beyond 10, it seems like these are really strange values that most of the data doesn't seem to be following. But we can also see whether there's skewedness from just the box plots. The top whisker is noticeably bigger than the bottom whisker, or the top rectangle is noticeably bigger than the bottom rectangle. Basically, this little split in the middle, which is our median, if that's the side to above is a lot longer than the side below, the data appears to be positively skewed or skewed to the right. If it's the other way, if there was a lot of values on the bottom but not a lot on the top, we would consider it to be skewed to the left. And the best way to do it is to take this plot we have here, turn it over to its side, going from 0 to 25. Here we see that part is stretching out this way to the right, so we know it's skewed to the right. This positive is going to be positively skewed also because it's a little bit too high. Here we get a bunch of outliers we might want to investigate and actually sort of talk about TV stuff. We may want to explore whether or not they're worthy of putting it in there, or did someone just put 24 hours to troll us? You don't know. Something worthy to explore in terms of that measurement validity. All right. That was a lot. I know. Take a short break, do a couple quiz questions, take a breather, and come back and we'll finish up. Ready? So, in this lecture thus far, I've had you all go through and find mean, median mode, find standard deviation, find that five number summary, look at graphics. One of the things you're going to get tested on, well, assessed upon this module, is how do I write up all these results? And that's going to be important. To write up these results, we want to be able to turn this stuff all into words. And to be honest, we did this a lot. I talked about these things bit by bit all throughout the entirety of what we've been talking about, our, our entire lecture, really. And that's really how a lot of these lectures are going to go. I'm going to break these things up bit by bit, and then we're going to put it all together to sort of see how should we write these things up. So the first part is we add a topic sentence. Time spent watching, TV can distract other activities such as exercise, meaningful activity. For that reason, it's important to monitor television time. Note, that has nothing to do with data. That has nothing to do with formal statistical social science analysis. It's just also just being, you know, thinking about it in terms of an opinion. Your opinions do matter. Using GSS data from 2018, our findings suggest that half the respondents are watching about 2 hours of TV per day with an average of roughly 3 hours. So about means 2.94, standard deviation 2.84. While the middle half of respondents reported watching between 1 to 4 hours, there were reported instances of some people watching TV for about 24 hours, which may be a cause for concern. System directions for the future. Time in front of the TV is not only a measure of screen time these days, and other questions need to be asked regarding time spent in front of the computer or on one's cell phone to get a better picture of time use and sedentary lifestyle. So that's one thing. So it goes beyond just the look at TV. From 2012 to 2018, actually, it seems to be that there was a decrease in television watching. But does that mean that we are now in this active running around lifestyle? Maybe not. Maybe the switch has been going from television to YouTube and going on to Reels or TikTok. That's something to really go beyond just the data and tell a story that has nothing to do with necessarily data analysis and more on your own pure social science, sociological understanding of things. I want to describe, if I'm going to describe these histograms, 1 to 2 sentences will do. I'm not asking for a lot for these things from you all. What I really want to do is say whether we have a skewedness level, skewed to the left, skewed to the right, and where do the values seem to be basically bunching up at. And while I'm giving you all a little bit of free reign to explain these things on your own, no, it should be pretty obvious where the boundary should be. In this case, it looks like it starts at 0, and by 10, I don't see a lot of data beyond that. If you wanted to say 0 to 5, I wouldn't actually have a problem with that. I would be fine with it. But after 10, then I'm going to be like, well, maybe you should be a little bit more careful in the way you're talking about the data. So most individuals between 0 to 10 hours fits what we're talking about. The box plots, you can also basically say 1 to 2 sentences, and are there potential outliers? The box plot seems to suggest it's positively skewed, and many respondents are outliers in terms of TV watching. I see a lot of dots here, so potential outliers seem to be fitting the bill here a lot. Overall, what I do every single module, especially going forward, module 2 through 7, this is something for you all to pay attention to. Okay? You want to be able to use the writing tips worksheet that I posted in the readings and materials thing in the modules tab of Canvas. So just to make that abundantly clear, I post this file for you all. This file is provided to you all, where I go ahead and I talk about these things, talk about examples, and then literally break down to a sample set of paragraphs. to get you a good understanding about really what am I looking for? When I'm asking you to write these things up, what am I really looking for? I recommend looking at this stuff, exploring what it says, and using it because that's a good key to scoring all the good points for this course. Likewise, as you're about to do your analyses for the first time, which is really, really cool, you're going to be dealing with Jamovi, which is very, very intimidating for many of you all. Don't fret. There's going to be both a guided worksheet and readings materials, as well as a Jamovi how-to video on how to do these things so that you feel at ease and good to go. And homework zero or homework problem zero on each homework will be a check to make sure that what I did in this section, as well as what's done in our Jamovi tutorial, that you all are able to get the same results as you can see there. Problem zero is basically no one's supposed to be doing anything. It's just to check your work to make sure you know what's going on so that you can replicate it and do amazingly on the other homework problems. Take a short break. Take a deep breath. We've gone through a lot of stuff. And for folks who math and stats are not their favorites, it's probably felt like a lot. I also go very slowly. So I want to make sure that like if you need to go at 1.5 speed because I'm talking slowly, cool. But don't stress too much. The main goal of this class is not to do this stuff by hand. I don't really care of the hand calculations. What I want you all to be able to do is to report on the data. If you can read and interpret Jamovi output, that's really what the whole point of this module will be. As a quick reminder, while I had you all download and install Jamovi 2018, those will be for the homework this week. For the blog posts, you'll be doing GSS 2024. This is now up in Module 2, and I will have a data sets little side module up in the getting started points, which will have the 2018 and 2024 readily available if you forget about it and need to get to it. 2024 is going to be for the blog posts, reminder 2018 for the homework. But you got this. Otherwise, that's all we got here. Thanks, you all, for this amazing next module. And if you have questions, you have concerns, shoot me an email. I'll get stuff graded. And good luck. Take care.